introduce Dr. Bhat from Sanjay Bhat from TCS Research. In his previous avatar, he was a professor at IIT Bombay, and he must have realized at some point that he can do research while making money, so he shifted to TCS Research. So let's hear his explorations on bandit optimization.
Thank you. Uh, so this title is not just meant to be a play on words, given the title of this workshop, but since we are talking about bandit optimization, certainly probability, learning, optimization, they're all in there. And yeah, I was not sure whether statistics, I can claim that statistics belongs there or not in bandit optimization. I did, yeah. So yesterday I was working on the slides, I had second thoughts. And explorations underlie kind of bandit theory. So that's the title. Now I knew that there were going to be students here. So the first maybe nearly 50% of the slides is just like a gentle overview of bandit literature. I hope the experts in the audience will bear with me for some time. But I believe I have something interesting to come after that. So the motivation. So I'm specifically my interest is on bandit problems where the decision space is continuous. Okay, and at least as far as I could tell, there doesn't seem to have been that much, relatively much less work on optimization on continuous decision spaces as opposed to discrete. I could be wrong, but at least going by what I've found, there seems to be a big skew in terms of bandit literature or with finite decisions and with continuous decision. Of course, linear bandits is an exception. So the motivation for this for us in our research team came from a dynamic pricing kind of a setting where imagine you have a seller, possibly in an online e-commerce setting, where your product, you're trying to sell a product which has a certain demand curve, right? So there's demand as a function of price. And generally we know that demand goes down with price. Maybe there are some luxury items where that does not hold, but and let's see. Let me try. Yeah. So the seller is interested in maximizing his revenue, right? So if you look at the demand, which was high there but low here, you multiply by the price, you get the revenue, but price is low here. So the revenue is probably going to have a maximum somewhere. And the seller is interested in selling at this price where the revenue is maximum, right? The only problem is he does not know the demand curve or the revenue curve. So he could conceivably try experimenting in order to see where the maximum might be, right? So he might offer the product at this price once, then at this price and so on. And what the seller is going to get at each of these prices is some noisy feedback of the revenue, right? Noisy because there's a whole population of buyers, and they may, some may buy, some may not buy at that price, and so on. So so this kind of sets up a dynamic pricing problem, which we could think of as a interaction between the seller and the market. Let's see, yeah, the seller and the market, which occurs in a sequential manner. The seller gives out a price, and the market responds by giving a revenue. And the seller's objective is to use at each time here is objective is to use the market responses to past prices to choose future prices such that the accumulated total revenue is as high as possible, at least in expectation, right? Now this, I'm sorry, yes, this fits in very well with a stochastic multi-arm bandit problem. Of course, in the previous case, I didn't say that the seller is restricted to choose from a finite set of prices, although in practice that is what probably he will do. But in the standard or classic stochastic multi-arm bandit problem, so we can abstract this setting out by saying that there's a learner interacting with an environment. The learner takes actions, the environment returns rewards, and the actions are chosen by the learner from a finite set of actions available to him. And the environment returned by the reward is depends only on the current action, right? So this is how this differs from the reinforcement learning in the Markovian setting, where the rewards could depend on the past in a certain sense. So the learner's objective is to use the outcomes of past actions to choose future actions such that the accumulated total reward is as high as possible. Now the word bandit, so came from, I got this from the book by Latimore and Chaba. So in the 1950s, researchers were trying to understand learning in animals, and they had experiments like this where a mouse would be released at this arm of a T-shaped maze, and randomly different trials, the food would be either on one arm of the one side of the T or the other, and they would observe how the mice learn, kind of the distribution of where it's going to be. And then they wanted to scale up to humans, but of course, even in those days, it was, I guess, not considered ethical to put humans in a maze and make them chase after cheese. So they tried two levered versions of a slot machine. So a slot machine with two arms, and sometimes the one arm would give better reward than the other. And these slot machines, I guess, for a long time have been called bandits, because if you have a sustained interaction with one such machine, the net result is that the money that you had goes into the machine, just like interaction with a bandit. So these are called one-armed, these began to be called one-armed bandit. And then if you have an array of these, then that becomes a multi-armed bandit problem. So there are two problems in a multi-armed bandit setting. The overarching problem is, in a loose sense, which arm is the best? Okay, so which decision? So imagine you have a learner who's pulling these, trying out these different slot machines at different times, trying to find out which one has a higher probability of giving a reward. So over a long time horizon, which arm is the best to try? But at each sequential decision, at each interaction time, you have one more decision, which is, given whatever I've observed till now, which arm I should pick next. Okay, so there's a decision problem and a learning problem. And examples, clinical trial, yesterday Professor Siddharth mentioned this, alluded to this. And this was also, I think, the original motivation for what is acknowledged as the first paper on bandit, or what we now call as bandit problem. This is a 1933 paper by Thompson, in which he was trying to address the problem of how do we assign subjects to a treatment. So you're trying to compare two treatments, treatment A and B, and you're running a clinical trial. So I think the conventional way of doing a clinical trial now is that you have two groups, and you assign one treatment to one group and the other treatment to other group, and then you let the treatments run their course, and then you observe what is the effect, what is the incidence of the disease or whatever, in the two groups. And then you use statistical methods to see whether whatever you observed is statistically significant. And based on that, you decide which treatment is better. But in this method, what happens is you might have unnecessarily subjected one group of people to the inferior treatment, right? So I think what Thompson was trying to do was, can we adaptively kind of decide, based on whatever. So people walk in, unlike the case, this batch kind of a setting where you assign treatments to two different batches. As people walk in, you assign them a treatment, one of these two treatments, you observe based on your experience, you decide which treatment to assign to the next person who walks in. So this is I think the setting that Thompson was exploring. Another well-known example is that of recommendation. For example, music recommendation, right? You have a music streaming platform, and as users walk in, you decide which music to recommend to them, and your reward is, of course, if the recommendation is accepted, then that's like a reward for you, right? So here also the problem is which song to recommend next. Now, bandit problems are like the gold standard, so to say, for uh, capturing the dilemma between exploration and exploitation, right? Which is what is facing our restaurant goer here. So do you go to the your favorite restaurant, which you have been to many times? You know what kind of experience you're going to get. It's safe and you have enjoyed it. But then maybe there's a new restaurant opened up, which people say is good. Do you risk going there? If you go there, the experience is not does not work out, then you kind of regret, I wasted one day, one opportunity. On the other hand, if you don't go there, you don't know what you missed. Maybe you missed a better alternative, something which could have improved your future experiences, right? So this is the exploration versus exploitation dilemma, or a trade-off, which a bandit problem is captures in a very formal way, right? And you can study it in a very formal way. The number of, if you just do a Google Scholar search, so every time I give a related talk, I update this uh, little bar chart. So you see how the number of papers on bandit algorithms. I just do a keyword search for bandit algorithms in Google Scholar. This is how it has been growing. So it's a very, very active area of research. And there are, starting from the initial days, there are many, many variations on this that have come up. So I'm going to be looking at this general setting. Okay, so in each discrete time period, the learner chooses a decision from a decision set D, and I'm not at this moment telling you what the set is, and he receives a noisy reward. So the noisy reward consists of two parts. So there's a deterministic part which is determined by the decision through a function g, a deterministic function g, which however is unknown. And then there is a additive noise, and this noise is a sequence of zero mean independent random variables. So you could say that the mean reward is a deterministic but unknown function of the decision. Right? And you could have multiple objectives. You may want to learn an approximation for this function g, or you may want to go a little beyond and actually learn an approximation for the optimizer of g. And what we want to come up with is a policy or a rule that suggests what decision I should choose next based on decisions and rewards that have been taken, or decisions taken and the corresponding rewards observed in the past. And my motivation when we were working on this is the dynamic pricing example, where the decision is the price and the reward is the revenue. So a couple of special cases, if I let this decision set be finite, right, then I'm back in the multi-arm bandit case. And this function g is just a function that maps each arm to its mean reward. All right. In this case, the arms are assumed to be independent. Another popular variation of the bandit idea is stochastic linear bandit, where this D is a subset of some D-dimensional space. And this function G, the mean reward function, is a linear function of the decision vector. Right? So this is a case where you may say the infinite arms. So if you decide to call each decision an arm, then this is an example where the number of arms is infinite. But there's an advantage. Here there is no structure. Here there is some structure to the reward. So the advantage you get is if you have observed the rewards at certain arms, then imagine you can kind of fit this function, and that also tells you something about the reward you may receive at some other decision values, which you have not yet experienced. You have not yet taken those decisions, right? So there's an advantage here that comes from the structure. What I'm going to be specifically interested in is a slight generalization where the reward function is a possibly non-linear function of the decision, but it is linear in the parameter. It is linear in the unknown parameter. Okay. So there are two kinds of problems in the bandit literature. One is called pure exploration. This is the situation where imagine you're not really interacting with the real environment, but maybe you have some kind of a simulated setting. Imagine instead of actually selling those items at different prices, suppose you were to just conduct a survey, ask people, if I sell you this product at this price, will you buy it, yes or no? Okay. So I'm not actually selling, I'm just doing a survey. So if the person answers yes or if person answers no, there is no regret. I don't lose anything. However, there is certainly a cost involved in conducting this survey. So I may have a budget, right, on the number of trials, but each trial, whatever the outcome may be, I don't lose anything. So there's no point trying to consider the regret here. So this is called the pure exploration kind of a setting. And there are two ways in this can be done. One is a fixed budget. There's a limit on the number of people you can ask, include in your survey. And in this case, so at the end of the survey, you have to come back and say, I think this is the best arm. I think this is the best decision. This is the best price, right? Now the question is, it's not enough if you say that, you should also come back with a confidence level. I'm 80% certain that this is the best arm. Then an algorithm which gives you a higher level of confidence for the same level of budget is a better algorithm. The other setting is called the fixed confidence setting, where maybe your boss says, I want you to come back with a best arm with 99% confidence. And then you may say, okay, well, then I'll have to conduct at least 1,000 people, right? So you'll have to come back with the number of trials. And then a algorithm is better if it gives you an answer with the same level of confidence, but with a fewer number of trials. So this is the pure exploration setting. The other popular setting, of course, is that of regret minimization or exploration exploitation trade-off. Because here, if you explore more, that means you are taking more suboptimal decisions, and therefore you are losing out, right? You're taking more suboptimal decisions. On the other hand, if you explore less and exploit more, then you could possibly be stuck taking suboptimal decisions for a long, long time, right? So how to find the correct trade-off between exploration and exploitation, and that's the crux of this kind of setting. So I'm still going through my, kind of my introduction. Yes. Yes, the phi is known, the feature. I'm coming back to it. So I'll come back to that formulation in introduce it in a little more detail. Yes, yes, you can do that. Yes. But you'll see that I'm going to be working with in situations. I'll show you situations where that's not true. It's not one to one. Oh well, we'll see. I'll come back to. I'll allude to this point again. So the main ingredients for any solution in either setting essentially is you come up with sample-based estimators for the unknown parameters. So if in a finite arm, multi-arm bandit setting, the unknown parameters are the mean rewards of the arms, right? So you use sample means for those, right? Yesterday, Professor Siddharth was explaining the UCB algorithm, right? So you use sample means as the estimators for those parameters. In the linear bandit case, you actually use linear regression to estimate the unknown parameter vector mu, right? And so one ingredient is some sample-based estimators for the unknown parameters. Another ingredient is you now need finite sample convergence bound for these sample estimators. So unlike asymptotic results, which say that, okay, these estimators will converge to their true values as the number of samples goes to infinity, those are not usable. Those are not good enough for bandit problems. You need finite sample convergence bound. And typically these convergence bounds will behavior on the tail, depend on the tail behavior of the noise distribution, and typical assumptions on the noise distributions, for example, are sub-Gaussian. So many of the available analyses of different bandit problems assume that the noise is sub-Gaussian. So sub-Gaussian is a general class of distributions whose tails decay as fast as a Gaussian. And then the analysis typically uses these convergence bounds on these sample estimators to either decide when to stop if you are doing pure exploration, right? Or to cleverly trade off exploration with exploitation in the regret minimization case. Okay, so with this background, I'll now come to the problem that I am interested in. So in each discrete time, the learner chooses a decision from a decision set and receives this noisy reward. The mean of this noisy reward is a potentially nonlinear function of the decision variable through, but it, well, so this phi is a feature map, right? So it maps my decision space, which is d-dimensional, to a f-dimensional feature space, and f and d need not be equal. And so my mean reward is a linear function of this feature map through an unknown but constant parameter vector mu. And as before, eta is a sequence of zero mean independent random variables. As before, I could either I might want to learn an approximate or an estimate of this parameter vector mu, or I might actually want to learn an optimizer of this function g mu, right? So I mean, at the end, well, I mean, we like to now, whatever we do, we say we are learning. So, huh? Yes, that I'll make. So I'm going to, we considered the pure exploration setting, but we are now currently also doing regret minimization. I'll kind of maybe mention, yeah, I'll mention both. So my motivation for doing this comes from dynamic pricing. In the special case where I believe my revenue curve is a polynomial. So if my revenue curve is a polynomial function of the price, then I can absorb that into this setting by defining the feature map to be simply the vector of powers of the price. Okay, so this is the setting that I'm interested in. Now, we thought about it, we haven't reached there yet. Yeah, not, at least I'm personally am not clear about what's a good way to kind of bring that in also. But, I know, yeah. So here, to come back to your question, can we think of this as a one-to-one map? Now, if you think of this as a map from the interval, which is where the price lies, to my f-dimensional space, then it's not one-to-one. But if I restrict my attention to the image of this map, then I could consider it one-to-one. However, that image is not a very convenient thing. It's like a curve in f-dimensional space. It's not very convenient. So, for the sake of convenience, we will kind of not treat this as a linear bandit setting. So there are two ideas I want to introduce. All right. So I'm going to consider a pure exploration case where I want to find the optimum of this to within an approximation, right? I'm going to kind of make it precise. So there are two ideas I'm going to use. One idea is that if we know is that we can get approximate optimizers from uniform approximation. Right? To explain this idea, suppose my true but unknown function is this red curve. Okay, and I have a approximation, a uniform approximation to this red curve, which is the blue curve shown here. So what do I mean by uniform approximation? In particular, let me say that this blue curve uniformly approximates the red curve to within a tolerance of epsilon by 4, where epsilon is some number, right? What it means is if I shift this blue curve up by epsilon by 4 and shift it down by epsilon by 4, then my red curve, which I do not know, I do not know it. However, I know that it will lie within this strip bounded by these two shifted curves, q hat plus epsilon by 4 and q hat minus epsilon by 4. Okay, so my red curve lies somewhere in this band. And what I want to know, what I want is I want to set an interval which hopefully contains the the maximizer of this unknown curve, which is S star in this picture, and which I can say all the points in this interval are not too suboptimal. Okay, and here's how you can do it. Here's how you can do it. Suppose I take this blue curve, or equivalently, since this is shifted, this is just a shifted version, but it's easier to see in this cluttered diagram. Take this dashed curve, okay, which is just a shifted version of this blue curve. This is my estimate. So I know this. I have it in my hand. Take the set of, take the interval consisting of all points which are suboptimal for this dashed curve by no more than epsilon by 2. In other words, you take this top, come down by epsilon by 2, and look at all points for which this dashed curve lies above this level. That is this interval d dash. Okay, d dash. Now this d dash, the same applies for the blue curve also. All points in this interval d dash are suboptimal for this blue curve by no more than, they're no worse than epsilon by 2. Okay, if you take the, do you see that? That means the value of, so take a point like this here. Okay, this is certainly not optimal for the blue curve, but the difference in the function, how much you have lost as compared to the optimal, is not greater than epsilon by 2. If the optimal value is 100, you are not worse than 100 minus epsilon by 2. You're not below 100 minus epsilon by 2. So you're within the optimal value, within an epsilon by 2 of the optimal value. That's a better way to put it. Okay, so all points on this in this interval, the function value on the blue curve for those points is to within an epsilon by 2 of the optimal value of the blue curve. All this you can do because the blue curve you have in your hand. Okay, now for all these points, what can we say about the red curve? Now the red curve is, it's kind of captive, it held captive between these two bands. So the highest it can go is the peak of the upper dashed curve, and the lowest it can go on this interval is the bottom of this lower dashed curve, right? The highest it can go is there, and the lowest it can come is about here. What's the difference between this point and that point? It's at most epsilon, which means for the red curve, you take any point here and you see how you are doing with regard to the red curve, you are worse off by no more than epsilon. So you're within an epsilon of the optimal value of the red curve on this interval. Every point on this interval has this property, right? So all this can actually be proven So you can prove that if I take, if I have an epsilon by 4 uniform approximator, and I take the epsilon by 2 optimal points for that, then all these, then the set of these points will have two properties. This set will contain the optimal of the true but unknown curve, and every point here will be within an epsilon of the optimal value of the unknown curve, right? So this is one idea. Now the question is, how can we obtain such a uniform approximation, right? Now, for this linear in parameter setting that I'm considering, you see that, I mean, we can easily see that every estimate of mu hat of mu yields a uniform approximation. How? So this is the norm for the uniform approximation, right? The soup norm, which is just this. But this is just an inner product between mu minus mu hat and the feature vector at S, right? So you apply the Cauchy-Schwarz inequality, and you'll see that this is bounded above by this. This is the parameter error in the 2 norm, and this is the maximum. So typical applications, my set D is going to be bounded, actually compact in fact. So this will be some number. So this will be some number. So if I get, if this number is k and I find an estimate mu hat, which is accurate up to epsilon by k, then I will get a uniform approximation to within epsilon, right? Now the question is, how can we estimate this parameter vector mu? Well, because I have this linear in parameter structure, I can just use ordinary least squares, right? And that is done even in cases like a linear bandit setting. So you are referring to this figure. What is the smallest such set? Yeah, okay. But that will probably be specific to the kind of fee that you have, the family of functions. Yeah, yeah. We haven't thought about that. Okay, so what are we going to do now? So imagine you have a set of observations like this available: decision, reward, right? So you form this, I mean, this is standard ordinary least square, but just a recap, right? So you form this matrix, which consists of all these feature vectors as its columns. You take the rewards, put them in a vector, and then you look at so the OLS estimate mu hat of mu is given by, obtained by solving this optimization problem, right? What is, so look for the Z which minimizes this error, because this is what your model predicts and this is what you've observed. To find that coefficient Z which minimizes this, and it's easy to work out solution. One can also consider regularized least squares, where you add a regularizer term. Now the question is, how does the quality of the fit depend on the choice of training points, right? S1 to ST. Now this question, why does it come up? It does not come up if you're doing ordinary least squares in a regression setting, because both of these, the x's and the y's, are given to you in a regression, in a supervised setting, right? But in a bandit setting, you are deciding the s's, you are taking the decisions, right? So part of the data is generated by your algorithm. And here again, there's a trade-off. So do I use my decision variables, decision power, in order to improve the fit? But if I do that, I might end up actually choosing a suboptimal point, right? Incur some regret. But if my fit is not good, then I may end up getting incurring regret later on anyway, because based on my poor fit, I am trying to exploit points which are suboptimal, right? So this question, which does not generally come up in a supervised setting, comes up here. Does the quality of the fit depend on the training points, which are now being generated by my algorithm, right? So this is a point. So let us take a simple picture. Suppose this is the true curve, which is now linear. So I'm fitting a degree 1 polynomial, let's say, right? This is my true curve, and I can choose. So I just need 2 data points to fit a linear curve, right? So I get to choose where I get to choose these training points. Except that wherever I choose the training point, I'm going to get the value of the function, unknown function, but with some error. Right? I mean, you can do this in a probabilistic setting, but I'm going to explain it in the worst case setting here. Let's say the error is bounded by this, right? And here is the same bound on the error applies here also. So you can see that in the worst case, I might end up with this line as my fit, or I might end up with this line as the fit. Now, if using this fit, if I evaluate this my fit somewhere else, like for example, this point, then you can see that I actually get a lot of error, right? So I've actually amplified the error here. Can I do better? Can you suggest a better choice of training points for this example? Just the endpoints, right? So you see that indeed you can come up with a choice of training points which minimizes this worst case error. This is the worst case error occurring here. Now I'll show you an example. The same thing happens in the quadratic case also, right? So yeah. No, so the error is bounded. This is the error. The error occurs where you choose your decision point. So right, where you, so so I made a slight digression from the bandit setting. I'm trying to answer the question: in what way does the training, uh, error in the fit depend on the choice of the training points? I'm kind of slightly digressed to address this question, right? So, so the error is the same. The bound on the error is the same, but somewhere else, based on this erroneous data and your choice of training points, you have come up with a fit, and the error in this fit can be worse somewhere else. Did that answer that question? Did I answer that? Okay, let's see. This model? Yeah. Okay, but fine. So okay, so let me make another attempt. So you chose some. Oh, sorry. You chose some values of S, right? Using those values of those values of S, this value of R was corrupted by noise. Using that noisy data, supposing you collected 10 points. Using those 10 points, which corrupted with noise, you came up with a estimate of the parameter vector mu hat. So now your estimated function is mu hat transpose phi of S. Now this, you can examine the error. This fit is not exact. It is not exactly equal to mu transpose phi of S. There's an error. You can examine how this error varies with S. Now this S, where you're examining the error, may not be one of these 10 points that you chose, right? So what this example illustrates, you chose this as your training data, S1, S2. But if I look at the fit and examine the error at some other point, that error could be larger than the error that was initially put in. Okay, yeah. Now, it's kind of interesting to see the same thing in the second degree case also, because it's not so obvious. The linear case was very obvious. So you imagine you have this quadratic curve, right? To fit a quadratic curve, you need 3 points. So, and I say that just in the previous linear diagram, wherever I try to query this function, I get an plus minus epsilon error. So these are the plus minus epsilon bands around this function, and I need 3 points. Suppose I choose these 3 points, means I'm going to collect my data at these 3 points, use that data to fit a quadratic curve, and see how much error this quadratic curve has somewhere else, right? So again, here are two worst cases. Worst case fits, and again you see that, okay, here they meet the error bound, the fits meet my error bound, but somewhere else the error increases, is higher. On the other hand, now is it obvious here what I should choose as my training points? So it turns out for this quadratic example, we should choose the endpoints and the midpoint. And if you, so for the same error in the training data, the error in the fit now you see keeps everywhere between the plus minus epsilon band. Okay. Now this is not a coincidence. So let us quickly kind of write some maths to see how this happens. So to keep it simple, let us take the case where I'm going to choose as many points, as many training points as the dimensionality of my space, all right? And if I look at the least squares estimate, which is given by this, but except that now this matrix xt square, just for simplicity to see what is happening, right? So this cancels out, and you actually see how the parameter error depends on the noise. It depends on the noise through this, okay? Now with this parameter error, the error that I will get, what I call the testing error, that means the error between your fit, the fitted function and the true function at any points s or at any point z is going to be this. So this was the noise vector that was there in captured in the samples. This z represents the point where you are testing the goodness of fit, and this x is of course the decision variables that you chose, the training point. So the question is, can we now choose elements of x or these training points which determine xt so that this does not get too big, right? So you see what happens, the error which was there that kind of leaked through into your data, training data. Can you choose your training points so that you don't end up amplifying it, right? So all that depends on this. So that motivates the following two definitions. So these definitions are not because of us. I mean, these concepts are already there. So just to keep things simple, assume that you have a set that is not contained in any proper linear subspace. So it's really f dimensional, okay? So a set of points, a subset, a finite subset, rather with cardinality f, a set of f points of B is called a barycentric spanner for B if two things happen. First, you should be able to write every element z of this set as a linear combination of these f points. That's simple. But the condition is that the coefficients that you need to use to achieve this linear combination, I mean, those coefficients will depend on z, so that's why that dependence is explicitly brought out here. Those coefficients should be less than 1 in absolute value, less than equal to 1 in absolute value, okay? So then this is called a barycentric spanner. Equivalently, if I do this, x inverse z, where x, the column vectors of x are simply these points, then the infinity norm of that vector should be less than equal to 1, and this should hold for all points z that I'm trying to express as a linear combination of these points, okay? So as I vary z over b, this should remain below 1. Similarly, a set is called a volumetric spanner, a set of vectors x1 to xf. If the same thing happens, you can express any vector in that set as a linear combination of these f vectors, except that the coefficients now have to be, I mean, the sum of their squares should be less than equal to 1. So in other words, the 2 norm of this vector x inverse z should be less than equal to 1, right? And for the sake of being a little practical, we can, these notions can be relaxed. So in our work, we assume a LM volumetric spanner, which means you are allowed to now take more than F elements to make it a little easier for you to meet this constraint. You can use more elements. And what is that? Well, okay, the thing is, we of course we would like to, but that becomes a problem in itself, right? So on a case-to-case basis, you will have to see, but that should not hold you back from trying to solve our bandit problem, right? So in case you're able to find something less, something not as good, but something that you can still quantify in the sense that there are M elements and these coefficients, the sum of their squares is no greater than L, or the 2 norm is no greater than L. We would like L to be 1 and M to be F, but if you're not able to manage that, then we could still try to work with this. All right. So these notions are related to the theory of design of experiments. And we will be interested in case where this set B is really the image of our feature map. Okay, that's what we'll be really interested in. Now, there's an interesting, so this again a small digression. There's an, how much time do I have? 5 minutes? Okay, maybe I'll rush through this. So there's an interesting connection. Okay, so imagine you are doing a linear regression in an adversarial setting. There is a learner, so there's a learner and an adversary. So the learner has to choose F points from this set B. And what the adversary is going to do is, after observing which points he has chosen for training, the adversary will decide where this fit is going to be tested. Okay, so he will choose the number of testing points and the testing points themselves. And then the game, so once these choices are made, the game proceeds by saying that at the points chosen by the learner, data will be generated, right, at those points. So this mu is unknown to both the parties. So you generate mu transpose xi, but you corrupt it with noise. The noise has a variance sigma square, which is known to both the parties. And the noise samples are independent. So you generate this data, and then you use ordinary least squares to estimate mu. And having estimated this mu, you get an estimate mu hat, use that mu hat and calculate the mean square expected mean square error between the estimated and the true function at these points, right? Now this is little loaded against the learner because the learner moves first and the adversary gets to observe his choices. So just as a student, when preparing for an exam, he has to prepare for the worst case a question paper that may come. Here also the learner has to prepare for the worst case. So the learner would like to choose training points that minimize the worst case expected mean square error, where the worst case is over the adversary's choice. Okay, and turns out that the answer to this problem is the volumetric spanner for B. Yeah, he can choose any number of points, but it turns out that if actually there's going to be one worst case point, and it makes sense for the tester, the adversary, to just concentrate on that worst case. So you're right. So you kind of see and when this happens, the worst case also happens to be the volume one of the volumetric points only. Okay. And we kind of saw that. If you remember that linear example diagram, in that case, the volumetric points are precisely the endpoint. And the quadratic case that we saw, the volumetric points for that case were precisely the endpoints and the midpoint. And you kind of see that the worst case happens there, the worst case error, if you choose anything else, right? Okay, there's an interesting this thing for the barycentric spanner also. Yeah, yeah. We tweak the game slightly. So the learner still chooses the training points, the adversary observes this, but now the adversary has a noise variance budget. He gets to choose the testing points, the number of testing points, but he has a budget, noise variance budget, which he distributes over these points. Okay, he gets to decide how much noise. So now you generate data, except that at the ith training point, you generate data according to sigma I square. And the rest goes the same. In this case, it turns out, again, what training point should the learner choose to minimize the worst case error over the adversary choices? The answer turns out to be barycentric spanner. So we are specifically, I'm going to now come to the polynomial case. Question is, can we find these volumetric or barycentric points? And it turns out, yeah, so remember, we kind of took a slight digression and started asking the question, what are good training points to choose? Yeah. Yes, I did. And yeah, I'll give you two places where we use that. So in the polynomial case, so where my unknown function is a polynomial and I'm fitting it as a polynomial. So it turns out, so this was one of our contributions. If for this polynomial case, to try to find, if you do this, right, x inverse z, s is some place, you are trying to express phi of s as a linear combination of phi of P1, phi of P2, phi of PF, etc. It turns out if you try to do that, then the coefficients turn out to be the familiar Lagrange interpolation polynomials. Or I'm sorry, the fag ends. I don't. There's a very interesting connection here. So what was C of Z in the slide 2 slides ago becomes L. These Lagrange polynomials. So for these Lagrange polynomials, you have to choose these nodes, right? The interpolating points. And so if I choose them to be, for example, the unit interval equispaced points, point 0, 0.2, okay, this is not 0.2, but I have like 5 equidistant points, equally distributed points. Then you see that somewhere the Lagrange polynomial peaks, which means if I were to try to express phi at this value of f, as a linear combination of phi of this, that, and that, then one of them would have a coefficient that goes above 1. Okay, so this is not a volumetric or a barycentric spanner, but it turns out there's a set of equations, either algebraic equations you can solve, or you can set up a convex optimization problem whose solution will give you the barycentric points for the polynomial case. In fact, very interestingly, they also turn out to be volumetric points. So in the polynomial case, they both are the same. And up to degree 4 or 5, you can actually solve them by closed form. So if I do that, repeat the same thing with barycentric points, you see that all the Lagrange polynomials now are kind of bounded between -1 and +1. Not only are they bounded between -1 and +1, but if at any point I take the sum of the squares, that's going to be bounded between 0 and 1 also. So a quick listing of how we use this. So we use this with Thompson sampling. So in Thompson sampling is one way to do regret minimization in bandits. So a quick overview of Thompson sampling. So you maintain a posterior over the unknown parameter vector mu, right? So that means there's some posterior covariance matrix and some posterior mean. And the way Thompson sampling proceeds is you sample from that, treat that as your parameter itself, right? So that becomes your estimate of the function. Find the optimal for this estimated function. Remember, this is just a sample. So you find that optimum, you apply that optimum, that is your next decision, and you observe the revenue or reward that you get, and use this observation to update the posterior. Okay. Now the question is, and this continues, this is the crux of Thompson sampling, but the question is, where do you start from? You need to start with a prior, right? So what we did, we found, so this was an empirical study. We found that if you do one round of exploration at the barycentric spanner and use the resulting data to initialize the prior, then empirically you do much better in terms of regret. Okay, so that's given in this particular paper. And then we did, we use volumetric points for pure exploration, again in the polynomial case. Well, I mean, we have a general algorithm, but uh, it was motivated by the polynomial case. So this is in the so-called pack setting. That means with a high probability 1 minus delta, I would like to return. So you have an unknown function, and I would like to return with a set for which I can claim with high confidence that this set contains the set of epsilon optimal points for this unknown function, and it also contains the global optimizer. Okay? And so what we showed is that if you simply repeatedly explore this function at volumetric points, so essentially, kind of the math goes through, you can estimate. Uh, uh, so use our concentration bounds to decide when to stop, and when you stop, you do that what I was showing with the the red curve and the blue curve, right? So you stop, you take your estimated curve, you find the epsilon by 2 optimal points for that, and return that as your set. And with we showed that this will have this sample complexity and so on. So this is given in this paper. We are currently trying to do the same thing for regret minimization, where each time we kind of tighten the epsilon tolerance, and so that the sets get smaller and smaller and kind of concentrate around the true optimum. So we are currently analyzing that. Yeah, it's yeah, I don't remember very well now, but I hope not. Well, this is going to be a small quantity, so its logarithm is going to be negative. Right, delta would be close to 0, and you have 1 by 2 raised to f by 2. F is the dimension of the, kind of the degree of the polynomial. Yeah, delta small enough. I mean, certainly this quantity is going to be less than 1. So the log is going to be negative. Delta anyway has to be between 0 and 1, and you are dividing by a power of 2. Yeah. So these are, so this is my last slide. These are the people who are involved in this work. Chaitanya and Manu were at TCS Research. Manu went on to join IIT Roorkee. Chaitanya is doing his PhD at UIUC now. And Hitesh is currently a pre-doctoral apprentice at TCS. So that I'm sorry for overstepping the time. Yeah. Yeah, yeah. Yeah, yeah. The notion of volumetric points or volumetric spanners is related to this so-called John's ellipsoid, which is the smallest volume ellipsoid, I think, the ellipsoid of smallest volume that can contain a given set. So it's related to that. For your print. Why does it actually exist? How can you find very specific points? There's two of them. You can cover the whole space with that of yeah. You wanted just 2 points, so that the whole space is covered. Distance of any point from these 2 points is at most 1. Yeah. So in case of barycentric points, you can show that it exists. Why do you say 2? No, so for example, when f was 2. Yeah, yeah. The set will also 2 sides. Yeah, yeah.
But then there is improvement for the 2 points, it can cover the whole set. That's definitely sufficient.
Yeah, in case of barycentric, I believe you can show that they exist simply by using like compactness continuity arguments. So essentially, if you find a set of vectors which maximize the determinant of that matrix, so that is the same as the barycentric. Yeah, so I showed 2 papers. You can read them. Otherwise, you can.
That the basis of access that
Yeah.
that's more robust than something.
Yes, true. That's perfectly true. Yes. So, in fact, the worst case points are the endpoints, and you should include them in your training set.
It's the fact that you are choice of loss function.
Yes. Yes. That's correct.
Case study we provided. I was also finally understanding something. So my question is, how do we manage this explore versus exploit in our own research? Because like all the people who have come, people are citing from economics to like geometry, like in the same paper, they are citing both from physics. So like, how do you go about acquiring skills in all these areas? Because even when you do these online courses, they say that sometimes it's beyond the scope because these are PhD level work. So they just like walk over the technical details saying that it's beyond the scope. So any advice on that?
So your question is, how do you decide how many areas to explore before you stop, right? What my personal experience is, if you focus on a problem and kind of keep, I mean, generally, I found what works for me is to ask simple questions and see if you can find the answer to those. So either the answer could be already found somewhere, but more often than not, you will come up with a question whose answer is not. The question may be simple. It's not maybe worth writing a paper. I mean, may not result in a paper immediately. You start answering that question, and then you kind of naturally come up with peripheral questions and issues and so on, and you keep finding things that are related or which lead you further in this thing. So I mean, the barycentric thing, we asked a very simple question, started from a simple question. So and then when you are in the process of writing a paper, you naturally ask yourself, has this idea appeared somewhere, or are there other ideas which are related or connected? And that's how these other things that you mentioned, ideas from physics, and that they come at a later stage. This is what I believe. So if you pick a question and see what I need to do to find the answer to this question, things will start happening and keep happening. Right.